off yesterday? Did you guys write it down? What number and what page did we leave off on? Was it the termite problem? All right, so let's just, it's just because there's so many problems here that I want to try to just do something different each time. So let's see, number 2 there looks like it's bacterial. We've done bacteria. We've done population. Okay, let's do this one here. This probably looks like a population one, but it's different. It says workers instead of people. So let's do the coal one. Coal was once a booming industry in central Pennsylvania. However, the industry has begun to decline. In the year 1950, about 600,000 were employed in the local coal mines. Since then, the number of coal miners has declined by 5% every 7 years. How many coal workers were or will be employed in the year 2020? Ooh. So let's see if we can, let's write the function first, right? We want to know what workers, so let's call this one W, not because you have to, just because I want to. What is W going to depend on? What are the amount of workers going to depend on? Time, and what is time being measured in here? What unit? What unit are we measuring time in? In years. So after the equal sign, first comes the initial amount. Once this decline started, how many coal workers were there? 600,000. Times, we need a growth factor. Okay, for the growth factor, we start with 1. Is it growing or decaying? Is the number going up or down? Down, so it'll be minus the rate of growth or decay. What's the rate, Jason? 5%, so I'm going to write 1 minus 5. What am I going to write? Good. 1 minus 0.05 to the power of time. And I can simplify that to be 0.95 to the amount of time. But now we can get specific. Okay? We want to know the amount of workers, not necessarily after X amount of years, but after how many decay cycles. So the way you would find a decay cycle, so this 5% is happening every 7 years. Well, how many years are there for between 1950 and 2020? There are 70 years. Okay, so how many 7-year cycles are there in 70 years? 10. How'd you get that, Ann? 70 divided by 7. So I can, you can write 70 over 7 if you want, but I'll just put 10 is equal to the 600,000.95 to the 10th power. But the key is knowing that Mister, how'd you get 10? I don't get it. I don't see 10 years mentioned there anywhere. Yeah, I know. It's not about 10 years, but the cycle repeated itself 10 times. In 70 years, 7 years will pass 10 times. From this point, I would just do calculator. You can either, if you're really good with it and you can type it in all at once, that's fine. Oh, speaking of calculators, let me show you. I don't know if this thing is gonna work. I don't want to ruin this, but let's see if it works. I'm working on embedding some calculators into your e-class page. I hope you guys have your own calculator, but just in case, see, I'm putting like a graphing calculator here if anybody wants to, and I also have, but this one I'm getting it to fit. I'm putting a scientific one also, if anybody needs to use it. It's there. Don't say I don't take care of you. It's right on the E-class page. So let's see, 0.95 to the 10th power times 600,000. And we're measuring people. So can you have part of a person? So like I'm getting 359,242.163. But like let's say I were to get 0.999999999 of a person. Could you round up? Technically you can't because you need a full person. So it's how many whole people do I have working after 10 cycles? I have approximately 359,242 workers. Any questions there? You need what? Oh, that's just the equal sign. When you put away the equal sign, that just means you're rounding. That just tells the person that it's not exact. It's you know, this up here doesn't give me that exactly, but it gives it to me rounded. And the point I was making before is that you have to round down. It depends on what you're. Typically, usually when it comes to money, owed, if you owe somebody money, they round up. If you're talking about people or anything that has to be whole amounts, you round down. If it doesn't say otherwise, you can leave it up in there. Okay. Car depreciation we did. Wilma and Walder's Weaving Wonders. That's boring. It's just depreciation, rapid population, boring, baseball card. And, all right, let's do this one. I don't know. I haven't had a chance to read through this whole thing, but this is like supposed to be an activity. So I'm kind of curious how this is going to work out. I've never used this before. I just found it, and let's see if it's any good. So hooray for the after Thanksgiving sales. You go shopping with some friends, and that shirt that you had your eye on at American Eagle is 30% off. What percent of the original price is it? Okay, so we're talking about growth factor. If a shirt is 30% off, well, then what percent on is it? 70, yeah. What percent of the original price is going to end up being 70%? Did you already try this page? I know you're always ahead. Did you try this page already? Was it any good? Or was it kind of like confusing? It was okay? All right. If the shirt originally cost $38, how much is it going to cost now? How can I find that? Just multiply. So 38 times 0.7. 70% is 0.7. What does that give you? Okay, 26.6 exactly? Rounded? Okay, well, it's important because it's money. So it is 60 cents? 38 times 0.7. Yeah, I'm getting exact. I'm getting 26.6 exact. So as far as money goes, this is going to cost $26.60. Okay, so now let's say it's not really 30% off. If it was only 4% off, what percent of the original price would you be paying? 96%. If the shirt originally cost $38, how much would it be now? Well, 0.96. Because the thing is, when you're talking about how much something costs, you don't multiply it by what's being taken off. You multiply it by what's being left on. So if something is 4% off, it's 0.96 on. And there I'm getting $36.48. So the values that you found are called multipliers, blah, blah, blah. You can read that part on your own. It's probably going to be the same. Oh, okay, this is the first part. They're just showing you two different ways to do the first one. And now what if you are at some early bird special sale and the shirt is 30% off, but then because you're there, it's another 30% off whatever the sale price is. How much would the shirt cost now? So what happens if you're paying 30% off of 30% off? Well, it doesn't state, but let's just say the shirt still costs $38. If something is 30% off, what percent on is it? Yeah, 0.7. So that'll give you the sale price, but then if you tack on this early bird special, that will be times another 0.7, or 0.7 to the second power. See, well, it's easy. First you calculate, and then you take another. So, and then it tells you it's 1862. What if you get to the register and now not only is the shirt on sale, and not only do you get the early bird special, but you find a coupon and you get another 30% off? Well, then that's what this tells you. It's just every time you get 30% off, you multiply it by 0.7 on. What might you be able to do instead? This is what gets you going towards exponential functions. This is the same thing as saying 38, which was the original price. Okay, remember, think of what we're doing with exponential or growths and decays. This is the original amount, and what we used to call A, times what's the growth factor here? Or in this, I guess in this case, it's the decay factor, because it's what percent of the shirt were you paying? Huh? 7%, 0.7. And in this last scenario where you had all the discount on top of discount on top of discount, how many times did you multiply by 0.7? That's the same thing as saying times 0.7 to the third power. That's what's getting you used to thinking exponentially. Do you shop at American Eagle? Does that even exist anymore? Yeah, maybe. You like, but not the stores? You don't shop there? You only shop at Foot Locker? I shop at Walmart. They got good stuff at Walmart. If you said you could have done 38 times 0.7 to the third, then you're correct. If we had another 30% off on top of that, besides, well, if you don't get kicked out of the store, what would that look like now? If we already have 38 and then times 0.7, but then you had those 3 discounts, and then you got another discount for being friends with Caleb, for just if you mention Caleb's name at the register, they give you another 30% off. What would it look like now? Instead of 0.7 to the third, you'd be paying 0.7 how many times? 4. This is a basic kind of exponential equation. Blah, 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 to generalize. Oh, so here we go. Look, final amount is equal to original amount times the multiplier. What did we call the multiplier? And the original notes, what did we call the multiplier? The growth factor. And then to the power of, put time, but here it says number of times. How many cycles are we going to go through? In this case, the cycle is the amount of coupons. Okay, I'm gonna stick away from this because we have better things that you can do that stuff on your own time if you want. This is just different types of sales, multiplying by different things. I think we've had enough practice with that, so let's just keep on going through this stuff. Of course, the whole idea of exponential equations is not only good for sales on close. Exponential situations occur all the time in the real world. For example, think about the last time you went to the doctor for a sore throat. They may have done a throat culture. Have you ever had that before? That swab in the back of your throat and you want to throw up everywhere? To see if you have strep throat. You don't like strep throat, Decay? What they do is swab with a giant Q-tip to see if there's organisms. If there are any streptococcus bacteria, they'll reproduce in the dish until there are enough to really see that they're there. This works because bacteria reproduce by dividing, which means their population doubles each time they divide. So let's say you've got a culture that doubles every hour. Okay, we saw that yesterday. What is that double gonna mean? If something is doubling, what's that double? What did we call it yesterday, and what did we just finish calling it a minute ago? We called it a growth factor yesterday. What did we just call it now? The multiplier, yeah. And every hour would be the time. So if you started with 55 bacteria, that's the original amount. How many? Oh, do we know that the growth factor they just finished telling us is 2, and it doubles every hour. How many hours are there in 1 hour? How many hours are there in 1 hour? It's 1. Yeah, so for that person, you would just put a 1. How many hours are there in 2 hours? 2, yeah. How many hours are there in 3 hours? 3. So I'm not here. Well, I won't calculate those, but just for fun, let's calculate the last one. After 50 hours, if this continues, what would happen to that 55 bacteria? Well, that's going to be fun. It's going to fill up your screen. 2 to the 50th power times 55. Yeah, it's going to give it to you in scientific notation. So that's like a 6.192449488, but that's times 10 to the 16th, which means you'd have to move the decimal over to the right 16 places. Spaces. This is where exponential equations come in handy because the population is doubling. What is our multiplier? We just said that. What's the multiplier if we're doubling? 2. So now we can use our new formula. Yeah, blah, blah, blah. We knew that already, 50 hours. Okay, we just finished doing that. Okay, here you go. Somebody not named Marquise, tell me, what would change in our formula if the population tripled every hour? It's not a double rainbow, it's a triple rainbow. What would change in the formula? See how they wrote basically the same formula I did? So instead of doubling, if we tripled, what would change in the formula? The multiplier, the growth factor. Be careful if you put exponential into the equations in the calculator. Remember to follow order of operations, okay? More practice. In 1985, let's do cell phones. In 1980, you don't like cell phones? No, you love cell phones. In 1985, there were 285 cell phone subscribers in the small town of Centerville. The number of subscribers increased by 75% per year. Write a function and determine if this example is a growth or decay, and then how many cell phone subscribers were there in 1994. Okay, so let's do, I hate using S's because my S's look like 5s, but all right, let's do an S for subscriber. What does subscribers depend on? Time, we're measuring time in years. What's the original amount? 285 times. How can I determine what my growth factor is going to be? Well, it's increasing by 75%. So how can I determine what that growth factor is going to be? That's the growth rate. How can I determine what the growth factor is going to be, or what they call it? Yeah, it's the 1 plus. You got to do the 1 plus in front. Have we done these enough times where I could just from the beginning put 1.75 without confusing you? Is anybody confused if I just put 1.75 and you don't know where I got the 1 from? I won't mind. If you understand how I got it, I don't mind if you put that on your paper. But if you don't get it, I started with a 1. It's the same one I gave you yesterday. It's 1 that was right there, plus the rate of growth or decay. In this case, it's growing. Everybody loves cell phones, especially on trade deadline Thursday. To the power of, well, okay, we're measuring time in years. How many years passed by from 1985 to 1994? How many years passed from 85 to 94? 9. So let's try to use this to figure out how many cell phone subscribers. 1.75 to the power of 9 equals times 280 fizzle. So I'm getting 43. Oh, look, this is a pro. Oh, I love this one. Great one. Great number. Are you guys looking at the same number that I am on your calculator? Yeah. You should be getting 43,871. Look at that decimal. It's tempting. It's like 0.986. Ooh, round me up. Up, up. Can I round up? Why not? No, we're not counting cell phones. What are we counting? People. Yeah, we're counting people. We're counting subscribers. And you can't have part of a person unless they're really short. So you gotta round down. So I'm getting here that the subscribers 9 years past by is gonna be approximately you know what? I did this. I should have put in here instead of T, I should have put 9 because I had already plugged the 9 in from the beginning. 43,871. Yara, what does the little squiggly line equal sign mean? That I rounded down. That's a round down. Okay, let's do number 3. Number 3 looks good. While breathing, everybody likes breathing. About 12% of the air in the lungs is replaced after one breath. Write an exponential decay function if the initial amount of air in the lungs is 500 milliliters. How much of the original air is present? So, like if I just breathe in, I breathe in, I have 500 milliliters in my lungs. So what this is saying is that with every new breath, it's not like your lungs are completely wiping out and replenishing itself. Some of that old air is still there. So they want to know after 5 breaths, how much air from that original breath 5 breaths ago is still hanging out and doesn't want to go home. So let's do I don't know what, A for air. What does air depend on? Does it? Yeah, it's breath, so I'm gonna use a B. This is just, it's all academic. It doesn't matter what. You can put X's and Y's, you put whatever you want. So the amount of air depends on breaths. And actually, since I don't have space, since I know how many breaths am I gonna take? 5, so I'm already gonna put the 5 there. So the amount of air after 5 breaths is equal to how much air did I originally have? Yeah, we're measuring in milliliters. Like if I were to put my answer with a unit, it'd be in milliliters. It'd be 500 times. What is my growth factor here? Or in this case, the decay factor. Decaying. Huh? Good. Whoa, Marquise, you're skipping way too many steps, man. I don't see 0.88 there anywhere. Well, if 12% is being replaced, how much old air, if there's 12% new air, how much old air is there? 0.88, yeah, it's the 1 minus the 0.12 to the power of 5 breaths. I don't have too much space, so now these are milliliters, so I could have partial milliliters. So I'm gonna, and it doesn't tell me where to round. So I'm gonna round to this and say it's approximately 263.87. Remember that part of this lesson, starting with yesterday, was also making sure you know how to use the calculator. So if you're not getting the same number on your calculator as I'm getting on my calculator, say something now before it's too late. And listen, for the last couple of minutes, let's do this then. Did Ann or anybody else that went home yesterday and worked on this? You didn't go home, I think you told me you did. Just part of it. Oh, you didn't get this far? Yeah. Oh, okay. Well, is there, even if it's one that I already passed, did anybody go home and work on this and reach something that they just had no idea what they were doing, and I could maybe go over that one before we leave? Was there one that you got to that was tricky for you that you didn't understand? It's long, I know. I don't expect you to do all of it, but I just had the material, so I just gave it to you, and you can kind of pick and choose what you want to do there. Well, if you do decide, I mean, you do have an assignment this week. Yes, question? Okay, number 2, the one I just passed? Okay. All right, we'll just finish there. But anyways, what I was saying, if you do decide to work on more of these, I'm available tomorrow before school, and also tomorrow we have the computer, so I can still help you with this too. Joseph invests 400 in stocks that double every year. So that double is the multiplier. That is the growth factor. How many years? You don't need to know that. That's yes. Okay. That's a good question. For how many years? That requires you need to know the inverse operation of an exponential, which is something called a logarithm. As far as I know, we don't do logarithms in Algebra I. Okay. The only way it can be calculated is by doing a log, unless you can find a common base. But you don't have to worry about things that actually define time. Do you still want me to do the one of 15 years, or you got no? You got okay. Yeah. Unless you know what you could do though, you could I guess do it by hand. So like you would do if it's doubling every year, you could do like okay 400. No, but now you wouldn't be able to because it's not gonna hit evenly. It's gonna be a decimal. Yeah, you have to do something called a logarithm.